So I think we had done. We were, I think, on this question number 25, right? We had actually done that as well.
Mhm.
So just 1 second, let me. So we have to start from question 26. So now let's try and focus on question 26, which is that they have. So now they're saying that the diagram shows the formation of compound Y from compound X in a chemical reaction R1 and R2 are alkyl chains. So these two over here are your carbon chains. So these are your carbon chains, and which row about this reaction is correct. Now, the conditions that are given for this reaction are HCN, and KCN is used as a catalyst for this specific reaction. So I'm just going to explain quickly what this reaction is. I'm going to explain it over here. This is, we're going to revise this as well. This is nucleophilic addition of aldehydes and ketones. So this reaction is specifically for aldehydes and also for ketones. What happens in this reaction is that you have whenever you have a carbonyl group, which is C double bond O, and it doesn't really matter whether it's an aldehyde or a ketone. The carbonyl group has a polar. It's a polar. The carbonyl compound group is polar. It has oxygen being electronegative. It's partial negative. The carbon is partial positive. So because of that, what happens is that nucleophiles, which are things that are species that are attracted to positive things, they tend to get attracted to these to this uh, to this carbon. So there is attraction, the CN minus one, which initially comes from the catalyst. I mean, KCN is the one that initially provides this CN minus one nucleophiles. So CN minus one gets attracted to the carbon positive, and as this negatively charged ion gets attracted, the electrons over here are going to get repelled. Why are they going to get repelled? Because the Cn minus one is negatively charged, so the double bond electrons over here would eventually be repelled because of the negative charge that's coming from here. And when this happens, this is produced. The C and H, the Cn bonds at the bottom, and the double bond electrons get repelled and they go to the top. So this is what is going to be formed. That's your intermediate in this case. ठीक है Abdullah, is this clear?
Yes, sir.
So your intermediate is going to be formed, and in the next step, the O negative, which is above up there, this O negative gets attracted to the H from the HCN. So you can either show it like this: the H is positive, the Cn is partial negative. So the negative electrons over here, they get attracted to the H over here, and this bond over here heterolytically breaks away because this thing over here has a negative charge. So it's going to be repelled by the negative electrons over here. So the electrons over here get repelled, and at the end of the day, you get this thing. So I'm just going to copy paste this. So at the end of the day, you get this molecule that the Cn negative ion is reproduced, and the H over here, which you can see over here, it's going to get attracted to the oxygen. So an OH is going to be formed. So what would happen is that this is known as a cyanohydrin. And it's a typical reaction. It's a mechanism that you have to remember. This is known as your cyanohydrin. It's a carbon atom which has OH as well as a nitrile group both attached to it. Okay, is this clear?
Sir, I'm still confused. How did hydrogen get, paired with oxygen?
The oxygen is negatively charged. The H over here has a positive
Yes.
charge,
Oh,
so
okay, okay.
they're obviously going to get attracted.
Yeah,
I mean,
yeah.
this is one mechanism for nucleophilic addition that you have to memorize this. Okay, I mean, it's one of the
Right.
mechanisms for organic chemistry. You have to memorize this nucleophilic addition mechanism. So this one has to be memorized. So
So, sir,
whenever you have
basically,
yeah,
this is like a form of, this is a reaction, but this is the way we perform the nucleophilic addition. So
uh,
this is the format we have to memorize, right? The formula
you have to memorize the mechanism, like
mechanism.
how the reaction happens. The reaction is pretty
Yeah,
simple. It's just that whenever you see a serial bond O, a carbonyl group in an aldehyde or a ketone, that carbon is going to get attached to an OH and a CN if you react it
right.
with an HCN. So it's a reaction that happens with HCN. So
Sahi.
this is the mechanism of the reaction. I mean, the reaction is simple. It's this. If I just write the reaction, it's simply that you have a carbonyl group. So you've got C double bond O or R. You react it with an HCN molecule. NaCN is going to be your catalyst. And the product of this reaction is going to be that this carbon atom over here, which I'm marking, this carbon atom would change into RC, or the middle carbon atom would change. It would NOH will get attached to it, and a CN will get attached to it. Okay,
Right.
is this clear?
Yes.
So this is one of the reactions that you have to remember. So if you look at your question is exactly the same. You can, if we go back and have a look at the question, you'll notice that there's a carbon with an OH and a CN, and there are two R groups carbon chains that are attached to it. Okay,
Mm-hmm.
so that now I did it twice. I did the reaction twice. I did it with an aldehyde. Now, if you do it with an aldehyde, you get the same thing. You get an OH and a CN attached, but the carbon has one H at one end and a carbon chain at the other end. I mean, aldehydes are the ones where the carbonyl group is right at the end. Like after it, there's an H. Okay, Abdullah, is this clear?
Yes. Mm-hmm. Yes.
Achha, so you'll get this type of molecule. You'll only get one carbon chain. But if you do it with a ketone, the carbonyl group is right in the middle, which means on both sides there are carbon chains. And if a CN and an OH get attached to it, then there would be carbon chains still attached on both sides. So you'll get two carbon chains. So that's the whole question, whether it was an aldehyde or whether it was a
Ketone.
ketone. So I mean,
Sahi.
that was the question. So I mean, this is obviously for an aldehyde you get one carbon chain because on the other side there's an H,
There is an H.
and
Yes.
for a ketone you get carbon chains on both sides. So the answer to this is that compound X must be a ketone, right? And
Yes.
the mechanism is nucleophilic addition. So it's going to be option. So this one is going to be option C. Is this clear?
Mm-hmm. Yes.
Okay, just a second. Next one, you have this question. Now you're saying in this question you can assume that H1 and H3 have the same chemical properties. So they kind of, I mean, they're obviously the same element, so they're kind of exactly the same. You've got H1 and you've got H3.
H3.
They're isotopes.
Yes.
The only difference is that they have different number of neutrons. So he's saying a sample and they have different masses because this has 2 neutrons and this one has 0 neutrons. I mean,
Sahi.
H has 1 proton. This one also has 1 proton.
Right.
And then it says that the sample of ethanol contains only one isotope of H. A sample of ethanol contains only one isotope of H, which is this one. This one. It's
Mm-hmm.
this one. It is reduced to compound Z So it is getting reduced to compound Z in a nucleophilic addition reaction using NaBH4. All the hydrogen atoms in the NaBH4 are the H3 isotope. Compound Z is then oxidized back to ethanol and water. Which statement about the final mixture of products is correct? As a first thing, let's first because again it's about aldehydes and ketones. So remember this. Let's do it over here. Remember this, that you have an oxidation process which you also have to memorize, which is that if you have a primary alcohol, that primary alcohol turns into an aldehyde. And I think he was talking about an aldehyde. I mean, the question he was very specific. One second, where's the question? So he was talking about an aldehyde, which is ethanol. The double bond O is right at the end. So he was talking about an aldehyde. Primary alcohols turn into an aldehyde, and aldehydes, they get further oxidized to carboxylic acids. Okay, so let's revise oxidation very quickly. What's a primary alcohol? Primary alcohol is the one where the OH, an alcohol is an OH. The carbon is bonded to the carbon. This is known as the alpha carbon, the one that has the functional group. There's only one carbon chain attached to it.
Yes.
So that's a primary alcohol. And this particular carbon would first turn into, I mean, this one over here, it would first turn into an aldehyde.
Okay.
So this carbon atom would get oxidized, double bond O, it would lose H and O would be gained. So it's, one second. So it's going to be turned into an aldehyde. This one.
Yeah.
And then this same carbon would then be further oxidized to a carboxylic acid. So that is oxidation. And there's another oxidation which is for secondary alcohols. For secondary alcohols, the oxidation is that secondary alcohols turn into, Zahib, can you hear me?
Yes, sir.
So they turn into ketones. So for example, you have a secondary alcohol which is carbon, OH. The alpha carbon is bonded to just one H, and on two sides there are carbon chains.
Right.
And this particular carbon atom would turn into a ketone. It would turn into double bond O. So since the double bond O is right in the middle of the chain, so that is a ketone. So this is oxidation of primary alcohol, secondary alcohols, and there is no oxidation of tertiary alcohols. They're not oxidized. So for them, there is no oxidation whatsoever. Now the conditions, you have to remember the conditions as well. What are the conditions that are used for oxidation? You use KMnO4 or K2Cr2O7, potassium dichromate 6. And they're going to be acidified. And you reflux. So those are your conditions for oxidation, and we can copy paste those conditions because those conditions could be used for all of these oxidations. So I'm going to copy it over here as well. 1 second. So for all of them, the same conditions can be used, except for the additional conditions that could be used for oxidizing aldehydes. I mean, if you want to oxidize aldehydes specifically, then the additional conditions are for this one and this one only. One is tolerance. Now tolerance has silver ions, and it's basically Ag plus NH3 two ammonia ligands are attached to it. So the overall charge is +1. This is a complex sign, which you don't really need to know at the moment. So it's Ag +1 ions. It contains Ag +1 ions, and in this case, the result is that you get a silver mirror. And the second one is filling.
So, sir, this is for primary alcohol to aldehyde or aldehyde to carboxylic acid?
Only this arrow.
Oh, okay.
For aldehydes, you've got three conditions. I mean, this works for every oxidation, right? You
Yeah.
KMNO4, K2Cr27, acidified and reflux. Whenever you want to oxidize something, these are good oxidizing agents. They're going to work. But for aldehydes, you have these two other oxidizing agents. These are also, I mean, they can oxidize as well. Felling has copper 2+ ions in its solution. Um, and we can write it. In this case, you get a silver mirror. That's your observation. Or a black precipitate. I'm revising the whole of the oxidation thing. For felling, the result is that you get a red precipitate. I mean, felling is Benedict solution. It's actually blue in color. So this felling solution is blue, but it changes into a red precipitate when you heat it with an aldehyde. And hopefully you know what the colors of KMNO4 and K2Cr2O7 is whenever they react. This goes from purple to colorless. This goes from orange to green. And there's one additional thing that you should know about, that if you want to stop the reaction at aldehydes, what you need to do is don't reflux. When you reflux, things can't get out. I mean, you put a condenser on the top, so any vapor, it condenses back and falls back into the container. So if you want to stop here, you use distillation instead of reflux. Like if you don't want the reaction to proceed further, and you wanted to stop at aldehydes and not make carboxylic acids, you're going to use distillation instead of reflux to stop here. And for that, and how would distillation help? Because aldehydes have a lower melting point, boiling point compared to alcohols and carboxylic acids. So as soon as they are formed, they're going to evaporate, and you can sort of take them out of the mixture. You can just, I mean, the vapor can be extracted and it could be separated from the mixture. If you put a condenser on top, you reflux, then the vapor will not come out. It would fall back into the container and the KMNO4 will further oxidize it to carboxylic acid. Okay, is this all clear?
Yes, sir.
Just a quick revision. Just one. So coming back to this. The question was, a sample of ethanol contains only one isotope of hydrogen. I said we didn't do the opposite. I mean, this question required the opposite as well. The opposite is that you can actually reduce them. Reduction is you go in the opposite direction. So reduction would be going from carboxylic acids back to aldehydes, back to primary alcohols. So I can kind of make an arrow over here. So going back to aldehydes, and the aldehydes can be further reduced to primary alcohols. Similarly, your ketones can be turned back into your secondary alcohols. So that is reduction. The reverse is reduction. Now for reduction, you use two things. You use NaBH4 or LiLH4. That should be enough. Conditions are not important in this case. This one as well, NaBH4 or LiAlH4. That's used for reduction. So these are used. NaBH4 or LiLH4. For carboxylic acids, they're kind of harder to, sorry. For carboxylic acids, they're kind of harder to reduce. So if you want to reduce them, only LiLH4 would work, not NaBH4, because that's slightly a weaker reducing agent. So that is reduction. And for aldehydes and ketones, because remember he's talking about aldehydes, what he's doing is this part. We're going to focus on this part, that he's saying that the compound is reduced to compound Z. So you started off with ethanol. So we are at this point. We've got an aldehyde and we're trying to reduce it back to an alcohol. So I'm just going to discuss the mechanism of this. Remember, we have an aldehyde, so we are reducing it back to an alcohol. Now the reaction without the mechanism, that's simple. You got an aldehyde. This carbon will have 3 hydrogens, so that's your aldehyde, and we will reduce it with NaBH4 or LiLH4, and a primary alcohol would be formed again. So what you just have to do is you have to turn the acetyl bond O back into an OH. That's it. So it changes back into an OH, and you have to add the hydrogens as well. So that's reduction happening. Hydrogens getting added. So that is reduction. TK, is this clear?
Yes.
Yes, sir.
Okay, so we are focusing on this part, an aldehyde turning back into a primary alcohol. That's it. Now, the mechanism of this reaction, remember, there's only one mechanism that we have studied for aldehydes and ketones, and that's nucleophilic addition, which we did discuss in the previous reaction. This is the only mechanism that aldehydes and ketones have, that they have a polar acetyl bond O. So what's going to happen over here? What's the mechanism? So you should have some idea of what the reduction mechanism is. It's exactly the same as nucleophilic addition. What happens is that you should have some knowledge of what NaBH4 or, for that part, LiLH4 are. Now Na has no role whatsoever. It's basically BH4 minus 1 ions. What is BH4 minus 1 ions? BH4 minus 1 ions are that boron is in group 3, so it shares 3 electrons with 3 hydrogen atoms. But that does not complete its octet. Like it has 6 electrons right now, so it forms one dative bond with an H minus 1 ion. So electrons from H minus 1, they get attracted to boron to complete its outer shell. So now it has 8 electrons. Boron had 3 electrons, shared one with this, one with this, one with this. It got 6 electrons. It still needed 2 electrons to complete its outer shell, so it got 1 electron from H minus 1. Now this BH4 minus 1 ion is your source for H minus 1 ions. So it releases H minus 1 ions. So it produces H minus 1 ions. What happens to those H minus 1 ions? Remember, you had an aldehyde. You had acetyl bond O, and you had H. What happens is that this carbon is positive. So just like nucleophilic addition, the H minus 1 is a nucleophile. This H minus 1 is going to get attracted to the carbon, which is partial positive. And as it gets attracted to it, the electrons over here are going to get repelled, right? And the same intermediate would be formed, which is going to be CH3. And H would get added at the bottom. There's going to be an H already there. And the O at the top would turn into O minus 1. It would turn into O minus 1. And similarly, since there is water or it's an aqueous solution, or the H over here are positive, so there might be an H positive that would be in the solution, and that would get attracted to the O minus 1. And an alcohol is formed back again. So this is the mechanism of this reaction, that it is nucleophilic addition. The BH4 minus 1 ions or the AlH4 minus 1, it's a source of H minus 1 ions. The H minus 1 ions, they attack the carbon atom, which is already polar, it's partial positive, and it bonds with that carbon atom. And when it bonds with that carbon atom, the electrons over here, because it's a negative ion, the electrons in the pi bond over here, they get repelled to the top, and it forms this intermediate. So this is exactly the same reaction mechanism as the nucleophilic addition mechanism that we did, where you had a Cn minus 1. the Cn minus 1 would come in and join, and the oxygen became negatively charged. Is this clear?
Yes,
Yes.
sir.
अच्छा, अब next जो चीज है ना, that's where's the question? The question was over here. Now he was saying okay, there were two isotopes of he's saying in this reaction you can assume that H1 and 3 have the same chemical properties. So, and he specifically stated that what did he state? He specifically stated that all the hydrogen atoms in Na, this line over here, that all the hydrogen atoms in NaBH4 are the H3 isotope. So, and a sample of ethanol contains only, so this ethanol contains only H1 isotopes. So going back to our mechanism, right, this one. This contains, I mean, this over here contains only the H1 isotopes, right? And the H that is coming from NaBH4, these are your H3 isotopes. So how many additional H got added to it? I mean, there was this H, the OH, right? That is coming from outside. And this H already that is attaching from the bottom. So these two are your H3 isotopes because they are coming from your NaBH4. Is this clear?
Yes, sir.
Okay, because NaBH4 is reducing them, so all the additional H atoms are coming from NaBH4. So he's saying compound Z is then oxidized back to ethanol. Which statement where the final mixture of products is correct? So let's continue from this point. Okay, this question is slightly more complicated. So you've got an alcohol now, and that alcohol has an OH, an H over here, and an H over here. So I'm going to mark the H atoms that came from outside. So that's the one with the 3 isotope. This one is also this is also the one with 3 isotope, right? Now you're trying to oxidize it back into a carboxylic acid. So when you try and oxidize it back to a carboxylic acid, not a carboxylic acid, I think to an aldehyde. Let's just quickly check the question. So you're oxidizing the same alcohol now back into an aldehyde. Which statement of the final mixture of products is correct? So if you try to change it back, this molecule over here. So we're trying to change it back to an aldehyde. What would happen is that the OH would be gone. It would turn back into, so you get two options now. If you try to, I mean, the H would be lost, right? So you'll get two options, CH3. The O would turn back into a double bond O. So the H3 isotope that got added at the top is going to be lost. Plus another one would be lost, and that's going to be one of the two H atoms. So it could either be this original H atom or it could be this H atom. We're not sure. So your product could either have the one isotope or it could have the 3 isotope, because any one of them could be lost. Is this clear?
Yes, sir.
And the rest of the thing, that's going to be water that would be formed. So two of the hydrogens are going to be lost. One of them is definitely going to be the 3H over here. So now we're going to try and answer this question. This question was a lot simpler. I went into the mechanism just to revise it. Just remember, the quick answer was that your aldehyde turned into an alcohol, right? So that means there were two H atoms that were coming from NaBH4. Those were your 3 isotopes, because he did tell you in the question that the H in the NaBH4 has the 3 isotope in it. So the H that came and connected with the aldehyde to form an alcohol, they were your 3 isotope. And when your alcohol got oxidized back, this H would be lost again, and one of this H would be lost again to form the aldehyde. So this H3 would be gone, and one of this H would be gone. So your water molecule that is going to be formed after oxidation could either have both of the H atoms that are lost can come from the 3 isotope, or one of them. I mean, this one is definitely getting lost, so it's going to be 3 isotope, and this one could be lost. That would be your 1 isotope. So let's look at the options now. The options are both ethanol and water contain H3 atoms. That's probably not true because both ethanol and water contain. I mean, that's not 100% true. I mean, it can be possible. But if this H and this H are lost, then ethanol will not contain the H3 isotope. If this H and this H are lost, then ethanol will contain one of the isotopes would be H3. So that is not 100% true. So what's the next one? Then he's saying ethanol is the only product containing H3 atoms. That's also not true because one of the H3 can be lost and could form water. So that's not true. Containing water is the only product containing H3 atoms. He's saying it's the only atom that contains, as the first statement makes sense. If you look at all the statements, he's saying at the end of the day, both ethanol and water would contain H3 atoms. That looks to be correct. Why? Because, I mean, that looks correct. H3 is lost, and this H over here is lost. That would form water, and there's going to be one H3 that would be left in the aldehyde. But let's quickly go through all the options. Ethanol is the only product containing H3 atoms. No, the other one can also contain H3 atoms. Neither ethanol nor water contain H3 atoms. That's definitely wrong. Water is the only product containing H3 atoms. Which final mixture? So both of them can contain H3 atoms. That's the only option that kind of looks correct. Is this question clear?
Yes, sir.
Because that's probably the only option. This one is slightly confusing because you have to go through the whole mechanism of you have to go through this entire mechanism of the reduction of an aldehyde back into an alcohol. TK, is this clear?
Yes, sir. You can hear me, right?
Yes. That's the next one. Ethane dioic has the formula this. What is the formula of aluminium ethane dioate? That must be easy because, I mean, it's a carboxylic acid which has H on both sides. So if it has H on both sides, it's going to be CO minus 1 on this side, and there's going to be CO double O minus 1 on this side. So whenever carboxylic acid reacts, the H is lost, which means that you get this ion, aluminium is +3. Okay, that's how salts are formed. Whenever you have a carboxylic acid, this is the way that salts are formed. So this entire thing is C2, and they're O4, and the charge is -2. And aluminium is +3. So if you do crisscross, it's going to be 2 aluminiums. So they're going to be 2 aluminiums, and the C2O4s would be 3. So option D is going to be your correct option for this question. So ये clear है?
Yes, sir.
अच्छा, which reaction gives butanoic acid as one of its products? The next one is, okay, which reaction gives butanoic acid as one of its products? Butanoic acid. Remember, alkaline hydrolysis can never produce butanoic acid. Why? Because the alkali would react with the acid. So you'll get a salt of the butanoic acid, not butanoic acid itself. So the answer is going to be C. That if you have ethyl butanoate, it's an ester, C double bond O, and there is O, and it will have it's ethyl, so that's 2 carbon atoms on this side, and butanoate, that's 4 carbon atoms on the other side. It's going to break in the middle. This side would turn into a carboxylic acid, so there's going to be 4 carbon atoms. And this side would turn into an alcohol, which is going to be, which will have 2 carbon atoms. So a carboxylic acid would be formed, but not in alkaline hydrolysis. Be careful, alkaline hydrolysis, and what happens is that the acid ends up reacting with the alkali. So you always get a salt of the carboxylic acid. For example, the alkali is NaOH, so it's going to form not carboxylic acid, it would form a salt of the carboxylic acid. TK, is this clear?
Yes, sir.
As the next one is which when reactants X and suitable reagents product Y and Z are formed in infrared spectrum of X. So reactant X is treated with a suitable reagent, products Y and Z are formed. So X is something that produces 2 things. It produces Y and Z when there's a reaction that happens. So 2 things are being produced, and the infrared spectrum of X is being done. So if you look at the infrared spectrum and products Y and Z, you've got infrared spectrum of both. And he's saying which row could be correct. Now he's given you 3 options. I mean, you can have a look at the options first. There's an alkene, there's another alkene, there's an alkene. Now when you do oxidation of alkenes, strong oxidation, the molecule splits up into 2 different products. So this could either be strong oxidation of an alkene. And what's the rule for strong oxidation of alkenes? That whenever there's strong oxidation of alkenes, the double bond is going to get completely broken into 2. It's going to split up, the double bond would break, and when the double bond breaks, you get 3 options. One is that after the double bond breaks, if the double bond carbon atom had H atoms attached to it, it would turn into carbon dioxide and water. The other option was if the double bond carbon atom has a carbon chain on one side and H on the other side, it would turn into a carboxylic acid. So the carbon atom would turn into a carboxylic acid, it would turn into double bond O and OH. And the third option is that your double bonded carbon atom, if it has carbon chains on both sides, it would turn into a ketone. So you've got 3 options. And that is strong oxidation of alkenes. Zaib, is this clear?
Yes, sir.
Just a second. So that's strong oxidation of alkenes, splits into 2. But then you've got the fourth. I mean, that's alkenes, TK, splitting into 2. The fourth option is an ester, and esters have. I mean, we can eliminate esters very quickly. Option D can be eliminated very, very quickly. Esters have a acetyl bond O and O group in the middle. An ester also splits into 2. It turns into a carboxylic acid and an alcohol molecule. So, but it can't be an ester because if you look at the infrared spectrum of the original molecule, if it were an ester, and let me open the data booklet. TK, where's the infrared spectrum? Make second. This one, absorption. TK, bonds vibrating, they're getting absorbed at different frequency. If it were an ester, there would be a C-double bond O, right? And there's going to be a strong absorption at the 1600, 1700 range in amides, ketones, aldehydes, and esters. So C-double bond O usually gives a strong absorption in this range. But there is no absorption, so it's not an ester. So that's one thing that we can eliminate. It's not an ester. Is this clear?
Yes, sir.
I said, then what are you getting? So it's definitely an alkene. I mean, the options that you have, it's definitely ABC. It's definitely an alkene. That's just what I can do is I can just figure out what these are. I'm getting a very broad, I'm getting absorption at 1600. So that's definitely a acetyl bond O. So I'm looking at the products now. So this one over here is definitely acetyl bond O. Because that's what the data booklet said. Acetyl bond O, 1600, 1700 strong absorption. Then you get a very strong and very broad absorption around the 2500, 3000 mark if there's an OH of the carboxylic acid. So you get a very strong and very broad absorption. So go back, have a look. You get a strong absorption over here. So that kind of indicates that this is an OH absorption that belongs to the carboxylic acid. Say be clear?
Yes, sir.
That means this product Z is definitely a carboxylic acid. Okay, that's definitely a carboxylic acid. So you have, I mean, you got choices B and C. I mean, D was already eliminated because X was not an ester, right? So Z is definitely a carboxylic acid. That's done. So what about this one? Is this a carboxylic acid? No, it's. I mean, you only have options between B and C now. So is this a carboxylic acid? This is not a carboxylic acid because you don't have a broad absorption at the 3000 mark. So Y has only two choices. It's either propanone or carboxylic. And now carboxylic acid is eliminated because Y is not a carboxylic acid. So the only option by elimination is going to be B. Saib, is this clear?
Yes, sir.
अच्छा इसका बस ये कर लेते हैं कि we can sort of just for revision I can sort of go through B and we can try and figure out are we getting the same products or not. So it's 2-methyl pentuene. So I'm going to draw 2-methyl pentuene, although we have our answer. Pent means 5 carbon atoms, tuene means there's a double bond on the second one, and it's 2-methyl, so that means there's a methyl group over here. And you can add in the hydrogens. There would be 3 over here, 3 on this side. This will have 1H, and this will have CH2, and this will have CH3. What's going to happen is try and oxidize it. If you try and oxidize it, strong oxidation, double bond would completely break. And when it breaks, the molecule splits into two. Let me just copy those parts. So this molecule is going to split into two parts. Okay, that's one part. And the other part is this one. So that's my second part. Now, if the carbon which was making the double bond has carbon chains on both sides, it turns into a ketone. I mean, that's the rule. So it's going to turn into a ketone. And if the carbon that was making the double bond has one carbon chain, then that turns into a carboxylic acid. It would turn into acetyl bond O and OH. So this is going to be formed. So it's going to be propanoic acid, which we are getting propanoic acid. And the other one would be a propanone. It's 3 carbon atoms with a double bond O right in the middle. So that's a ketone. So yeah, is this clear?
Yes.
So 1 second. Now coming back to the next section B पे आ जाते हैं कि this is about Kc. So you've got a sample containing 17.15 moles of HI, and it's in a dynamic equilibrium with 2.27 moles of H2 and this many moles of I2 in a volume of 1 dm cube and 141. Two equilibrium constants Kc and Kp can be calculated for this mixture. Which statement about the equilibrium constants for this mixture are correct? Now, most of the values are already given. That's for this question. You're given the equilibrium moles. I'm going to write those equilibrium moles 17.15 moles of HI. That's already given. 2.27 moles of H2 and I2, that's 2.84 moles. So Zahib, do you have a calculator? Can you tell me what the value of Kc is? It's going to be HI concentration squared. So that's going to be 17.15 and it's going to be squared. divided by the reactant concentration, which is 2.27, multiplied by 2.84. What do we get for this?
$45.62.
Kitna?
45.62.
So it's coming out to be 45 point. And would it have any units?
No, sir.
I said no units. This statement, the first statement is definitely correct. It's got no units, right? Neither Kc nor Kp, because the expression is because you have the same number of terms in the numerator and the denominator as well. So the terms are exactly the same. So it's not, they're going to get cancelled out. Concentration squared into divided by concentration into concentration. I just बात किया with statement about the equilibrium constant. The first is correct. 45.62. That's also correct. ठीक है. So that is correct. And then he's saying that Kc is greater than Kp. So we have to calculate Kp now as well. Now Kp is slightly more time consuming. It's going to be, because in Kp you have to find the partial pressure. So if I try to calculate Kp, what's the partial pressure of HI? What are the total number of moles? Can you quickly tell me what are the total number of moles?
$22.2.
I said 22.2. So it's going to be 17.15 out of 22.2 into the total pressure, which is 141 kPa, right? And that's going to be squared. I mean, mole fraction multiplied by the total pressure divided by 2.27. As it's going to be 2.27 divided by what? इसको सही कर लें. As it's going to be 2.27 divided by the total 22.2 into 141, right? kPa. और फिर उसको multiply करना है किससे? The other one, which is 2.84. And that's going to be divided by 22.2 into 141, right? Over kPa. Now, one thing, remember, if the number of terms above and below are equal in kP as well, you don't need the pressure because all the pressure terms are going to get cancelled out. ठीक है Zahib, is this clear?
Yes, sir.
Plus, not only the pressure term, but the total moles के साथ जो आप divide करते हैं, that would also get cancelled out. Because it's at the top there's 22.2 squared, at the bottom there's 22.2 multiplied by 22.2. So all that, I mean, the number of terms are exactly the same. So remember this, that when you have numerator and denominator terms are exactly the same, you can just put in moles, that's it. I mean, you don't even have to find the partial pressure. And these two values are going to be exactly the same. So number 3 is wrong. Because both Kc and Kp are going to have exactly the same expression. ठीक है, is this clear?
Yes, sir.
अच्छा बस. As the next one, but this question, you have to save time on this. Remember this: whenever equilibrium constants don't have any unit, that means even calculating Kc and Kp, you can simply use moles. Even in Kc, you don't have to calculate concentration. Like Kc is concentration of products divided by reactants, but we were not calculating concentration. As this one, energy cycle is given, which expression can be used to calculate the energy change delta Hz. So delta Hz, what is delta Hz? One path. I mean, you're starting at this point. What is delta Hz starting? This is your start. So that's your start, and you have to reach this point. That's your end. So one path is this direct path, which is delta Hz. The indirect path is you go from the other side. So basically delta Hz is equal to what? Delta Hz is equal to, it's equal to delta HF of CH4 plus it's equal to delta HC of CH4. ये clear है?
Yes, sir.
अच्छा, so और 2 times करना है कि नहीं करना? Do you have to multiply anything with 2? Which I don't think you have to do that, because delta Hc of CH4 is this is exactly the enthalpy of combustion of CH4, 1 mole. And this is exactly the enthalpy of formation of CH4 elements turning into 1 mole of CH4, so that is also 1 mole. So it's going to be just 1 and 1, so that's it. So only the first option looks to be correct. That's the only one that kind of looks correct, but we can, I mean, that's the one that we are getting. So what about the other ones? Enthalpy change of combustion of carbon. So plus 2 times enthalpy change of, I mean, we can talk about those as well. Let me write down the expression first. Delta Hg was that you had carbon solid plus there was 2H2 gas, right? Plus there was 2O2 gas. I mean, this is this part, and they were forming CO2 and H2O, CO2 plus 2H2O. So we had to find this thing, delta Hc. What are the different methods that you studied in Hess cycle? One was that if you're given enthalpy of combustion, right? Because the second option is about enthalpy of combustion. So if you're given the enthalpy of combustion of carbon, and you're given the enthalpy of combustion of H2, and the enthalpy of combustion of O2, which is 0, and the enthalpy of combustion of carbon dioxide, which is also 0, and the enthalpy of combustion of H2O, which is also 0. So it's, if enthalpy of combustions are given, it's, I mean, these three are 0 because they don't burn. Or in simple words, it's basically, I mean, you can look at the equation, it's basically carbon getting burnt in oxygen to form CO2, and the 2H2 molecule also getting burnt to form H2O. So in simple words, it's basically enthalpy of combustion of carbon plus the enthalpy of combustion of H2 multiplied by 2. So option number 2 looks to be correct. Ye bhi clear hai?
Yes, sir.
And then you have another one, which is enthalpy of combustion of carbon monoxide. That is definitely correct because there is no carbon monoxide anywhere. So enthalpy of combustion of carbon monoxide, we don't need that. I mean, there is no carbon monoxide anywhere, so we don't need that. So that number 3 is definitely wrong. So many gases, what is this? Many gases do not obey the general gas equation at high pressure. Why is this? What's wrong with high pressure? What happens at high pressure? Okay, why don't they behave as an ideal gas? Like if you have a container and that container has, so it has a piston and there are gas particles, right? So there's gas particles in that container. अब मुझे बताओ कि what happens if I increase pressure, if I start to compress it? Why would it not behave as an ideal gas?
Because like the atoms, the particles are too close to each other. They are bumping into each other. This like
So
indicates
that's it.
that.
Let's assume that I've increased the pressure to a really high pressure, okay, and this piston has been compressed, and so now it doesn't behave like a gas because it's more like a solid. Particles are close together, tightly packed. So that is a behavior of. So I mean, it's not going to behave as a gas. And why would it not obey the general gas equation? Because the general gas equation states that PV is equal to nRT. So one reason it doesn't behave as a gas is that now the particles are tightly packed at high pressure. So gas particles are not tightly packed. I said, but why does it not behave the general gas equation? The general gas equation states that pressure is, like if you look at the equation and nRT are constant, you're keeping the temperature constant, you're keeping the number of gas particles constant, then pressure is inversely proportional to volume, right? Ye clear as a hip? Is this clear?
Yes, sir.
So the general equation states that if you keep on increasing pressure, what happens to the volume? It should decrease, right? Yahi hai na? If you try to compress it, the volume should decrease, right? But it would stop behaving this expression at very high pressure, because at a certain point, the gas particles would be so tightly packed that they would become incompressible. You keep on increasing pressure, the volume is not going to decrease once the gaps are gone. Is this clear?
Yes, sir.
So, number one is obviously wrong. Because higher pressure, I mean, you're not adding energy, so that's obviously wrong. If one is wrong, then two and three are obviously, I mean, by default, they're always correct. So at higher pressure, the volume of the molecule is a larger proportion of the total volume. Like if you compress it, then there are no gaps. Okay? Gases के अंदर what happens is that volume, if you talk about a volume of gas, the volume of gas is comprised of two things. It's the volume of the particles plus all the empty space, because most of gases, I mean, whenever you picture a gas particles have large gaps between them, so it's mostly empty space. So once all the empty spaces are gone, the volume of particles and the volume of gas kind of become exactly the same because all the empty spaces between them are gone. And at that point, the gas would become incompressible and it would stop behaving like an ideal gas. You keep on increasing pressure, the volume is not going to decrease because there is no space left. Plus, I told you at higher pressure, because the molecules are kind of close together, so they are going to experience greater intermolecular forces. Previously, gas particles were far away from each other, so they were not really attracting each other. But now, if you compress them, that's why things liquefy or they turn into solids when you compress them, because when the particles are really close together, they start attracting each other and they turn into liquids. सही है? Clear है?
Yes, sir.
अच्छा एक second. Now, this one. Which species can accept a lone pair of electrons to form a... so who can form a dative bond? The one that has incomplete outer shells. Boron has... I mean, boron can. Boron has 3 electrons. So it forms a bond with F. It forms another bond with F. Another bond with F. So it still has... and it still has room for 2 electrons. So it can. H plus 1... can accept a lone pair because H plus 1 has a completely empty shell. So if you have NH3, this N over here has lone pairs. And those lone pairs are going to get attracted to this H plus 1. So that's also true. CH3 can do the same, I think, as well, because CH3, its outer shell is gone. I mean, it had 4 electrons. So there was if there's a 4th electron for carbon, then it's a radical. But if it's plus 1, then that means there is no 4th electron. Like there's an empty space over here. So it can definitely accept lone pairs from somewhere. Like NH3N has lone pairs. Those lone pairs are going to get attracted to... they're going to get attracted to this. So all 3 are true, are correct. Because all 3 have 2 electrons missing. Next is a sample containing X moles of Al2Cl6 is dissolved in water to give solution W. What happens when you mix Al2Cl6 with water? It forms 2 things. It forms, Al2Cl6 is a dimer of AlCl3. If you react it with water, 2 things are formed. Aluminium hydroxide is formed, which is a white precipitate, plus HCl gas is also white fumes of HCl gas are produced. In order to precipitate all of the aluminium as its hydroxide, Y moles of sodium hydroxide are required. So he's saying Y moles of sodium hydroxide are needed. More of the alkali is added. More of the alkali is added to dissolve the precipitate, giving solution Z. So the precipitate of aluminium hydroxide dissolves back if more alkali is added. Which statements are correct? The initial pH of solution W is 7, below 7. That is true because it's an acidic solution that's going to be formed. The actual reaction is something like this. The actual reaction is that Al3 plus first, the detailed reaction is this one. That 6 water molecules surround it and it forms a complex. So it's basically like this. This is what happens. that you have I mean, this is how period 3 elements they hydrolyze, the chlorides hydrolyze. You've got Al3 plus ions, water molecules get attracted to this Al3 plus from all sides. As they get attracted by water molecules from, because water is polar, the 3 plus ion strongly attracts these water molecules. This is one of the reasons why aluminum chloride strongly hydrolyzes, because water molecules, the lone pairs on water molecules are very strongly attracted to the 3 plus. And the water molecules, the H is positively charged. The H is going to be repelled by the positive aluminium ion in the middle. The positive aluminum ion in the middle would repel the H, and which releases the H plus 1, which then combines with the Cl minus 1 that they were also roaming around in AlCl3 when you dissolve it in water, and they together end up forming HCl gas, which is the white fumes that are seen. So you get an acidic solution, and the water molecule continues to break down because it continues to get hydrolyzed. The OH gets attracted because it's negatively charged, the H positive gets repelled. So at the end of the day, you get aluminium hydroxide. So the initial pH of solution W is below 7. That one is true. And then it's saying y is equal to 3x. So y is equal to 3x. What does that mean? Y moles of sodium hydroxide. So if you want to form aluminum hydroxide, you need 3 OH ions. So what is X? X moles of aluminum chloride. So X moles of aluminum chloride means, like, if you have X moles of aluminum chloride, and this is, remember, Al2Cl6, that means the solution will have 2x moles of Al3 plus ions. So you got 2x moles of Al3 plus ions. Because one Al2Cl6 contains 2 aluminum ions. So your solution would contain twice the amount of aluminum ions. So if you want to add OH ions to this, there would be 6. One Al3 plus needs 3 OH ions. So 2x would need 6x. So this would be wrong. It's supposed to be 6x, not 2x. Because you have twice the number of, if it had been 1 aluminum ion, then you would require 3 OH ions. But since you have double the amount of aluminum ions, because one molecule contains 2 aluminiums, so the amount of OH ions required would also be double. And then you have the last one, which is more of the alkali is added to redissolve the precipitate, giving solution Z. So Z contains X moles of aluminum. That's also not true, because it's going to contain 2x moles of aluminum, because one molecule would produce double the amount of aluminum ions. So the last option is also not going to be correct. Say, be clear?
Yes, sir.
That's up in next 136. Nitrogen dioxide is a gas produced when petrol is burned in car engines. Which acids are made in the atmosphere as a result of the release of NO2? That's acid rain. Pretty much all of them are produced during the formation of acid rain. What happens is NO2 goes into the atmosphere, acts as a catalyst, starts oxidizing SO2 to SO3, and itself gets reduced to NO. NO again reacts with air to gets oxidized back into NO2. So you've got all these acidic gases. You've got SO3. You even got SO2 as well. Now we can actually. The first one is incorrect, because SO3, because he's saying which acids are made in the atmosphere as a result of NO2. If there was no NO2, so the result of NO2, the acids that are produced are going to be the ones that are made from SO3 or NO2. If there was no NO2, then SO2 is not going to get oxidized in the first place. So sulfurous acid would probably not be formed. as a result of the release of NO2. So the first one has nothing to do with NO2. The next of the two are directly produced by nitric acid. I mean, nitric acid is involved in the formation of these two acids. You be clear?
Yes, sir.
As the next one, in which reaction is the major product formed by nucleophilic substitution reaction? So what's a nucleophilic substitution reaction? That's a reaction of a halogenoalkane where you have Cl. We don't really care whether it's a primary, secondary. I mean, you have multiple types of SN reaction. Carbon is positive, Cl is partial negative. So 3 nucleophiles can kind of come in and attack this carbon atom. It's OH minus 1, it's NH3, it's got a lone pair, and there's Cn minus 1 as well. The C has, the C over here has lone pairs. So these 3 can come and attack the carbon, and the Cl would get repelled and would eventually break off. So in which reaction is the major product formed by a nucleophilic substitution of reaction? The first one is wrong because that is correct. That's the condition, KCN ethanolic. That is perfectly correct. I mean, those are the conditions if you want to substitute Cn minus 1 in place of Cl or a halogen. So the first one is correct. That's the conditions. Ammonia in ethanolic under pressure, that's also true. That would also, those are the conditions for ammonia. You can either heat it in a sealed tube at higher pressure or you can use ethanolic ammonia. The third one is hot concentrated NaOH. Now for NaOH OH ion substitution, you need NaOH aqueous, not ethanolic. So the third one is wrong. The conditions are wrong. It's not going to be ethanolic. Ethanolic leads to elimination. Ethanolic leads to an alkene formation, not substitution. Zahib, is this clear?
Yes, sir.
Or in excess of P reacts with Q in the presence of concentrated sulfuric acid to form R. So R in excess of P reacts with Q. So that's an ester being formed, like concentrated sulfuric acid. So that's definitely an ester getting formed. So P reacts with Q. So P is a carboxylic acid as well as it's an alcohol. So there could be 2 kinds of esters that could be formed. Q could be an alcohol. So the alcohol part would react with the carboxylic acid part to form an ester. Or Q could also be a carboxylic acid. The carboxylic acid part could react with the alcohol part. So since the molecule P contains both things, it could react with an alcohol, and at the same time it could also react with a carboxylic acid. So to form R. So that means carboxylic acid, alcohol. The third one is wrong. Can't be this one. You can't have a ketone. That's wrong. So by just looking at the first statement, Q could be an alcohol. It could either be a carboxylic acid. Yahan tak clear hai? Zahib, is this clear?
Yes, sir.
So then effervescence is seen when a piece of sodium is added to R. Effervescence is seen. तो वो जो ester बन रहा है ना R, it still has a carboxylic acid. That's why I mean effervescence is seen when a piece of sodium. Now sodium reacts. So the thing with sodium is sodium reacts with both alcohol. It does lead to effervescence with that as well, and it also reacts with carboxylic acid. Sodium is capable of reacting with both. So that indicates that if these two combine to form an ester, the R would still have an unreacted carboxylic acid. Vice versa, if these two combine to form an ester, then R would contain the unreacted alcohol. But in either case, R will still react with sodium. So both options are correct. It could be carboxylic acid or it could be an alcohol. So options 1 and 2, both are going to be correct. Ye clear?
Yes, sir.
Uske baad you've got 39, which is 2 carbonyl compounds have the molecular formula C3H5. It's H5, H6, I think. So 2 carbonyl compounds have the molecular formula C3H6O, and which reagents give different observations with these 2 compounds? Different observations. 2 carbonyl compounds have the molecular formula C3H6O, Remember, they're both carbonyl. Now, there are only two possible carbonyl compounds, 3 carbon atom. The double bond O could either be over here, or the double bond O could either be in the middle. So that means one of them is a ketone and the other one is an aldehyde, because you have C double bond O at the end, or you could have C double bond O in the middle. So those are the only two options that you can have. So which reagents give different observations? The first one will give different observations because KMnO4 oxidation, the first one will oxidize. Aldehydes get oxidized to carboxylic acid. The second one is not going to oxidize. So that is true. Felling, definitely true because that's also an oxidizing agent. Aldehydes will oxidize. Ketones are not going to get oxidized. Okay? So first two are correct. Oxidation part is correct. It's going to differentiate. And this one, alkaline aquacidine, that's also correct because one of them is going to react with, it's going to lead to an iodoform test. Iodoform tests are with CH3, C double bond O, where if you reacted with alkaline aquacidine, the CH3 breaks off to form a yellow precipitate of CHI3. Okay. Iodoform test is specifically for this group. It's specifically for CH3 next to a C double bond O. Over here, you don't have a CH3 next to a C double bond O. You have CH3, CH2 next to a C double bond O, but not a CH3 next to a C double bond O. Ye bhi clear hai?
Yes, sir.
So organic compound T does not fizz when carbonate is added. That means it's not a carboxylic acid. So T is not a carboxylic acid. So now compound T contains 27.6% by mass. What could be the identity of? So it's not a carboxylic acid. तो पीछे रहेगा आपके पास. You got these two options. That's it. Does not fizz with sodium carbonate. So one of them is an ester, the other one is an aldehyde. All you have to do now is which T contains 27.6% by mass. So it's all about moles now. So propanol is this thing. So Zahib, what's the oxygen percentage? It's 16 divided by the total, which is what? 15 plus 14, that's 29 plus another 12, that's 41, 42. 58, क्या बनता है ये? 3 carbons, that's 36. 36 plus 16, that's 52. 53, 54, 55, and 58. Yep. So ये क्या बन रहा है? What's this?
27.58%.
Get that? ये आ रहा है 27.6, right? And you can, so you can try the second one, ethyl butanoate. Uska, I'll just draw the molecule. That's an ester, obviously. C double bond O. But is 4. This is 1, 2, 3, and 4. Ethyl is 2, so that's 2. And you can add in the H atoms. These are all H atoms. So it's 2 oxygens, so that's 32. Divided by, what's the total? That's 6 carbon atoms, that's 6, 12, 72. 72 plus 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84. 84 plus 16, that's 100, and 116, that's the total, I think. Maybe I'm wrong, but you can double check this, okay?
The 7.58, the same as first.
ठीक है, so 1 and 2 both are correct. चलो ठीक है, let's ये फिर बाद में करते हैं, ठीक है? कोई और? ठीक है सर?